All right, so this week we'll pick up where we left off looking at vectors. Again, we've kind of done a lot with visual stuff, so we're going to stay away from that, and we're mostly going to look at numerical operations. Okay, much faster to do things with vectors if you don't have to draw a picture every time. Not saying a picture is a bad thing. A picture is actually pretty good for word problems, but if you just have basic problems, we want a simpler, faster way than drawing a picture. Okay, so the first thing we're going to start out with is what it means for two vectors to be equal. Okay, so I've got two vectors, v and w. Remember, there's two ways you can write a vector. You should either make the letter look bold, or you can put the arrow on top. Okay, so for two vectors to be equal, what it means is that the components of the vectors are equal. Right? It means that the horizontal components match, and so do the vertical components. Okay, so what I'm going to do is I'm going to sketch a picture, and I'm going to show you something that sometimes people get a little confused on whether or not the vectors are equal. But we'll use this definition to see whether or not they are. Okay, so let me just get a grid so I can draw it to scale. Okay, and we'll start here, go here. So there's one vector. And we'll start here and go here. Do those vectors have the same initial point? You think, Leo? No. Do they have the same terminal point? No. So some people say, well, they don't have the same initial, they don't have the same terminal, how can they be equal? Well, equal just means that if you were to measure the horizontal components and the vertical components, the horizontals come out the same and the verticals come out the same. Well, if we measure it, right 2, up 3 for the black one, right 2, up 3 for the red one. Those vectors are equal, even though they're not drawn in the same spot. Any questions on that? Okay, so next thing. That notation that I just used, your book calls this algebraic notation. You got a bracket, two numbers inside the bracket separated with a comma. Well, there's a third way we can write vectors besides drawing a picture, and that's called unit vector notation. Does anyone remember from last week what it means if a vector is a unit vector? Yep.
It has a magnitude of 1.
Exactly, it has a magnitude of 1. So this last notation, and the most common one that's used, is built off that idea. It uses vectors that have a length of 1. So what I'm going to do is show you two special unit vectors. These vectors are named I and J. So whenever you're naming a vector, you never want to use those two letters. I and J are special names when you're talking about vectors, and they're kind of reserved for what I'm doing right now. There's also one more when we get to 3D, that's K. So in general, the letters I, J, and K, don't ever use those to name vectors. Use any other letters you want. But I is a special unit vector, so it's 1 unit long, and it points to the right. Okay, so what does it look like? It looks just like that. It's a vector that is 1 unit long, and it points to the right. Okay, J is another special unit vector. It's also 1 unit long, and it points up. And that's what J looks like. It's 1 unit long, and it points up. So the idea of unit vector notation is we're going to take those we're going to take I's and J's, and we're going to kind of use those as building blocks. We're going to stack I's and J's together till we get where we want to go. So if you had an initial point here and a terminal point here, all you have to do is stack as many of the I's as you need to get over to the right, and then as many j's as you need to get up. And the notation would look something like 8i plus 4j. It would look something like that. I don't know exactly how many, I didn't count. But that's the idea. Okay, so we're going to use I and j to kind of build vectors. Think of I and j as almost like Legos. We're going to stack them together to build things. The first time I go through it, I'll draw it. After that, we don't need to sketch it. Okay, so let's see how we could do the vector 3, 4 using unit vector notation. All right, so 3, 4 means right 3, up 4. Okay, I want to end up at that point. I'm going to start right there. So what I'm going to do is I'm going to stack i's together until I get as far over as I need to. Okay, so I'm going to take this. How many i's am I going to need to stack together to get from the initial to the terminal point? Dylan?
3.
Yeah, we're going to need 3. And what I should probably do is change the color so they don't blend into the x's. All right. There we go. Okay, so I'm going to stack 3 of the i's together. So we've got 1, 2, 3. And that's the first part of writing this vector in unit vector notation. 3i plus, and now I just need to see how many j's I need. Okay? I need 1, 2, 3, 4. So, you know what, instead of copying and pasting, I'm just going to sketch it by hand. 1, 2, 3, 4. So what we've just done is we built the vector we needed out of i's and j's. And that, what I just circled, is how you write a vector using unit vector notation. Now, I moves to the right, j moves up. Does that mean we can only stay in quadrant 1? Caleb?
No, because it doesn't have to start at the origin. You could start like in like the bottom left corner of quadrant 3.
Okay, so we could start somewhere else. Let's say we always start at the origin. Same question. Yep.
Can you have like negative I, negative j?
Yeah, you can have negative I, which would bring you left. You can have negative j, which would bring you down. So you can travel anywhere you want to travel in the plane. So the kind of the fancy word for traveling anywhere you want is we say that the vectors I and j span, S-P-A-N, they span the plane, meaning you can get anywhere you need to go. So vectors I and j span 2D space. Now, if we wanted to get into 3D space, they do not. Okay? I and j would not allow you to move in 3D anywhere you want to go. You'd need one more vector that would allow you to come out of the board and into the board. And that would be vector k, kind of along the z-axis. Right now, we're just dealing with x and y. So, two-dimensional space, you need 2 vectors to span the space. 3D space, you need 3. Okay, so any questions on that? All right. So let's look at some formulas for adding, subtracting, scaling, and finding the magnitude. A lot of those we've already done visually, especially adding, subtracting, and scaling. But now we're just going to do it with numbers. So for what I'm about to write on the board, v and w represent vectors, and then alpha is a scalar. Remember, a scalar is just a number in front of a vector, like 5w. 5 is a scalar. Okay, so each of my vectors has a horizontal component and a vertical component. Now, for writing the formulas, I went back to the algebraic notation just because it's simpler to look at. But once you have an answer in this form, like if you get the answer that way, you can easily convert it to unit vector, just going like that. Okay, so you should be familiar with writing your answers both ways. Okay, if you want to add 2 vectors together, instead of connecting them like I showed you, the end of one to the beginning of the other, and then drawing a diagonal. Numerically, all we need to do is add the horizontal components, add the vertical components, and we're done. Okay, so no more worrying about having to do a sketch. To subtract vectors, same idea. But now we have to be a little more careful with the order, okay, because subtraction is not commutative. So if you subtract in the wrong order, you're going to get the wrong answer. So just pay attention to the order. This is V minus W. So the V components should come first, the x1 and the y1, and then you're subtracting from that the W components, the x2 and the y2. Okay. To do scalar product, like if I wanted to find 3V, what we would normally do visually is take V, stack it together 3 times, and there's your answer. Well, numerically, all you need to do is kind of distribute the scalar to each component. So if you were tripling V, triple the horizontal, and then triple the vertical component. Okay, now the one we haven't done is this one. Can someone remind me again what that symbol stands for? The double bars around a vector? Yep.
It's not the magnitude.
It's the magnitude, it's the length. So let's just go back to one of the vectors I drew earlier. And let's look at this one. So we had the vector 3, 4. I didn't actually draw it, but now I did. And I want to find the length of that vector in black. How do you think I would do that? Yeah?
You use Pythagorean Theorem.
Yeah, we use the Pythagorean Theorem. This side's 3, this side's 4. So use the Pythagorean Theorem, and there's your answer. So basically, the horizontal component squared plus the vertical component squared, add them up, and take the square root. That's exactly what this formula is right there. That's what I just said. Okay, so just the Pythagorean Theorem. We haven't talked about finding the magnitude of a vector earlier, but we've talked about the Pythagorean Theorem a bunch of times, so the calculation is something you already know how to do. Okay, so we'll go through an example where I give you numbers, and we'll do each one of those. Okay, so here's the vectors we're going to work with. V is 2i plus 3j. W is 3i minus 4j. And the first thing I want to do is add those up. Okay, no pictures. Don't draw anything. You don't need graph paper. Just, we're going to do it numerically. Okay, let's start by writing the answer in unit vector notation, and then we'll write it the other way. So Shauna, when I add V and W, can you tell me what my the I component, or the horizontal component would be?
So like actually add them. Okay. 5i.
Yep, so the horizontal is 5i. And I should probably get away from saying horizontal, because when you get in 3D, we just call it the x-axis component. Yes, in 2D, the x-axis is always horizontal. But in 3D, we might not think of x as horizontal. Okay, but however you want to think of it, that's the x-axis component. And what about the y-axis component, which in 2D is the vertical? Well, tell me.
Minus j.
Minus j. Can you put minus 1j? Sure. Minus j is also fine. Hey, writing it in the other notation, Juliana, how would we do that?
It'd be 5i.
So in the other notation, there's no letters.
It's 5.
5
And negative 1.
and -1. Okay. So that's how you write it the other way. So it's adding. Let's try subtracting. So now we've got V minus W. All right, so Leo, could you tell me what I get when I subtract W from V?
It would be negative I plus plus 7j.
Yep, plus 7j because we're subtracting a -4. And in the other notation, -1, 7. So with unit vector, you don't have to put the -1 in front of the I, but when you write it the other way, you've got to put the -1, because otherwise there'd be nothing there. Okay. Both of those vectors are what we call binary operations, because you need two things to make it work. Scaling, you don't. I'm ignoring vector W in this problem. I don't need it. To scale, you only need one vector. So we're just going to take V and scale it. Okay, so if I triple vector V, what would I get in unit vector? Yep.
6i plus 9j.
6i plus 9j. Okay. Any questions on how you would write that in the other notation? Okay, so that's tripling. And the last one we're going to do is also a single vector input. You only need one vector. We're going to ignore W. And that's finding the length of V. Okay, so just look at each component, square them, add them up, and take the square root. So we've got the square root of 2 squared plus 3 squared, which is the square root of 13. Always follow the rules you know with roots. If you could reduce it, go ahead. Square root of 13, nothing I can do. Unless they wanted it as a decimal, then I could just type it in and get a decimal. Okay. Any questions on that? All right. Okay, so remember that a unit vector is just a vector with a magnitude is 1. Okay, you probably already have that in your notes. Okay, what we're going to look at now is sometimes we're going to be given a vector. It's not going to be a unit vector, and we want to make it a unit vector. Like that vector in black. Let's pretend that this was a grid. I just drew units of 1 in each direction. And I'll put a circle there just so we can see somewhat clear. That circle is a unit circle. It's a circle with a radius of 1. That vector in black is definitely bigger than the radius of the circle. So that vector in black is not a unit vector. This vector in red, hopefully it's close, pretty close. That vector in red is a unit vector. It's exactly the length of the radius of the circle. So our goal is going to be to take that black vector and scale it down so it turns into the red vector. We just have to figure out how much to scale it by. So if that vector in black was 5 units long, what would you have to scale it by to make it 1 unit long? Yep, 1/5. You basically would take the vector and divide it by 5. Or multiply by 1/5, same thing. What if the vector was 10 units long? What would you scale it by to make it 1 unit? Yeah? 1/10. So you multiply it by 1/10, or just divide the vector by 10. So the idea is we're using this formula right here. All you have to do is take your vector and scale it. We're going to be scaling by a fraction. So like if you had the vector, just to do a simple one that I can do in my head, the vector 3, 4. That's a 3, 4, 5 right triangle. Well, we just said earlier, if the magnitude was 5, we would scale by 1/5. What does that really mean to do? We're just dividing each component by 5. I took 1/5 of each number, and that would be the answer. So what I've just done is I didn't change the direction. All I did was make the vector shorter. So it was exactly a unit vector. All right, so if you understand that, you really don't need to write it, but this is the idea of what we're doing. We're finding a new vector. It points exactly the same way. We're just forcing it to be 1 unit long. How do we do that? This formula, right there. To find a unit vector, you take your vector and you divide it by the magnitude. If the magnitude was a 5, you divide by 5. If it's a 10, you divide by 10. If the magnitude of it is v, you divide by the magnitude of v, whatever the magnitude is. And that will force it to be a unit vector. Now I think this is actually basically the problem I just did. It's going to involve a 3 and a 4. Doesn't matter which quadrant you draw a 3, 4, 5 in. It's a 3, 4, 5 all the time. So the numbers here, it's really what I already showed you. Okay, so if I was going to find a unit vector for that, my first step would be find the magnitude. Well, I already know it. 3 squared is 9. Negative 4 squared is 16. 9 plus 16 is 25. Take the square root, 5. So now I ask myself, 5 units long. Is that a unit vector if it's 5 units long? No. So we need to adjust it using that formula. Take the vector that you have and divide by its length, or scale it by 1 over its length. So ours is 5 units long. We would scale by what fraction? Yeah. You'd scale it by 1/5. So you end up with 3/5 minus 4/5. Only difference between this problem and the quick example I showed you earlier, it's in a different quadrant. That's why one of them is negative. Okay, so any questions on how I figured out the magnitude was 5, why I scaled it by 1/5, and how I got 3/5 and negative 4/5? Okay, so that's how you find a unit vector. Okay, so I think the last 2 things in this section are word problems. First one's pretty straightforward. Second one's a little more time consuming. So what we might do is skip the second type of word problem, and we'll focus more on a word problem in a later section. Probably tomorrow or Wednesday for you guys. All right, so for this section, the word problem, the easier one, which we're going to do, is called a velocity vector. So when you're talking about velocity, remember there's 2 things you have to describe: speed and direction. So what we're going to do is come up with a formula where if I give you information like I threw an object at 60 miles an hour at an angle of 30 degrees, give me the velocity vector. Okay. We're going to come up with a formula to do that. Okay. A couple assumptions that we're going to make. Really, when I throw an object, it doesn't go in a straight line if I throw it at an angle. It's arcing, right? Because gravity is bringing it back down. We're going to assume, just to make this simple, that you do this in outer space, far enough away from any planets that gravity is negligible. Okay. We're also going to assume we don't have any wind resistance, because really when you throw an object, wind resistance is also slowing it down. Not a lot. If it's a sphere, those pass through the air pretty well. It's not like dropping a piece of paper where there's a lot of wind resistance. Okay. So a couple of things we're going to ignore just to make this a little simpler. So pretend like that's the path my object is traveling. I throw it, just goes in a straight line forever. No gravity. The idea is when you throw this object, okay, in black, think of this board as, well, think of it as what it is. It's 2-dimensional. What directions is that black ray that represents the path of my object, what directions is it moving in? What directions is that object moving? If you had to describe how it's moving. Abby? Okay. Anything else?
To the right.
And to the right. Okay. It's moving in two directions at the same time. It's moving up, but it's also moving to the right. So what we want to do is kind of separate that out. We want to focus on the right part and the up part separate. Visually, if you add the horizontal to the vertical, you would get what's in black. But we're going to kind of separate them out. And that is going to be my angle. Okay, let's call the horizontal component x, and that would be y. So we have two other vectors, x and y, that represent the components of vector v. Okay, let's start with x. I want to come up with a formula for x. So I want to involve this, and that. What trig function could I use that would involve the three things that I circled on the board? Yeah?
Cosine.
Yeah, you can use cosine. So cosine of my angle equals. Now, we've got to be careful how we write this. When we set up a trig function, cosine is adjacent over hypotenuse. But what about the adjacent? Like the color of the adjacent, how heavy the adjacent side is, like what is it about the adjacent? Yeah?
The length.
The length. Okay? So it's the length of the adjacent. And when we're talking about vectors, what do we call length? Yep. Magnitude. So the cosine of theta is the magnitude of the adjacent over the magnitude of the hypotenuse. And now my goal is to get x by itself. So we would multiply each side by the magnitude of e. Okay. So now we've just created a formula for the horizontal component. It's the magnitude of v times the cosine of theta. Okay, and ultimately what we're kind of doing here is we're writing something like this. Yeah. We have a number in front of I plus another number with a j. That's kind of what we're trying to come up with. We're trying to write this vector in ij notation, unit vector. So we have to figure out the horizontal and the vertical components. We just figured out a formula for the horizontal. Does anyone have a guess, without setting the whole thing up, what the formula is going to be for the vertical? Yep, yep.
Magnitude of v times sine theta.
Exactly. It's going to be the same thing except with sine, because sine is opposite over hypotenuse. You would set it up. You'd still multiply both sides by magnitude of v. And there's your formula for the vertical component. Now, just plug those two boxes in to that formula, and that will basically give us what we're looking for. So let's bring this up. Now, let me do one more step before I show you that, just to kind of make the connection between the formula you're about to see. So you would have magnitude of E, cosine. I called it theta in my diagram. I think your book calls it alpha in the formula. We can change it to theta, just as long as you understand it's an angle. Plus magnitude of V, sine theta. Okay. they both have a magnitude of v in common, so we can factor it out in front. And that's what the final version is going to look like. Magnitude of v times cosine of the angle I plus sine of the angle j. Again, I can change it to theta. It won't match what's in your book, but that's fine. So magnitude of v, that's the initial velocity of the object. Theta is the angle you're throwing the object at. Okay, so really, you just broke it down into a right triangle and found the adjacent and the opposite. And those are the two components. Okay, so for this section, we'll finish up with an example of that. And then we'll look at part of section 5.3. Okay, I'll show you the problem that we're going to skip. I'm going to skip it because it's more of it's a physics problem. I am going to do it in the other class because they have a whole extra day. And it's in videos from previous years. But for you guys, just because of time, we're not going to focus on the physics stuff as much. Okay. So here's our problem. Okay. Basically, you're throwing an object at 50 miles per hour at an angle of 30 degrees. Okay. Find the velocity vector. And then after you write that, I want you to explain to me what it means. Like if you can try to connect it to real life, what does the number in front of I mean? Once we figure it out, what does the number in front of j mean? Once we figure that out. Okay, so first thing I need is the magnitude. What's the magnitude of my object that I'm throwing? Okay. What's the magnitude? Yeah, so the magnitude is the initial velocity. So I really should have bars around that. So the magnitude is the initial velocity. So 50 miles an hour times cosine of my angle I plus sine of my angle j. Shauna, what's the angle I'm throwing this object at? 30 degrees. So cosine of my angle, put your unit vector for I, plus sine 30, unit vector for j. Now we have to do that out. Okay, so up to this point, you didn't really need a calculator today. You do for this part. 30 is a special angle, but in general, the angle could be anything. So it helps to have a calculator. All right, so I'm going to do 50 cosine 30. And I'm going to do the other part at the same time. 50 sine 30. So I get 43.3i plus 25j. 43.3i plus 25j. Okay, so there's the velocity vector. Now I want to understand what each component means. Anyone think they can tell me what this 43.3 means? If you were to really do this, throw an object at 50 miles an hour at an angle of 30 degrees. Yeah, it's the speed in the horizontal direction. So one way to think of that is if there was a wall in front of you and you threw an object just like they described, it would hit the wall at 43 miles per hour, roughly. Okay. If you were standing in front of the person throwing it and you pointed a radar gun at the ball coming at you, it would say it's coming at you at 43.3 miles an hour, not 50. Because they're not throwing it straight at you. Okay, there's an angle to it. The number in front of J, that's the vertical speed. So if you were in like a helicopter above the ball and you pointed a radar gun down, it would say the second the ball leaves the person's hand, like, right the very second they let go, it would say the ball is going 25 miles per hour up at you. Now, how come I said the second it leaves their hand? How come that wouldn't be the speed like 3 or 4 seconds after it leaves their hand?
Well, because like you said before, things arc, so it would start to slow down and fall.
Right, the vertical speed is going to slow down. It's going to arc. Eventually the vertical speed would be 0 at some point, and then it's going to start to come back down. So the direction of this object is going to go from traveling up to then back down. The horizontal speed would never change in a situation without any air resistance. Even with air resistance, that 43.3 is not going to change much. Okay? A ball is pretty aerodynamic, roughly, more than a piece of paper would be. That's flat, or like a sail on a sailboat. There's a lot of wind resistance, but that's intentional, so it catches the wind. A ball is not going to catch the wind too much. But that's the meaning of each component. So speed in horizontal direction, speed in vertical direction. And for most things, when you throw an object, the object does travel in a plane of motion. It doesn't really travel 3D, unless like you're throwing an object to someone and it's curving, which can happen. Then it might be traveling up towards the person and maybe to the left or to the right, curving as it gets there. Like a frisbee would probably do that, but when you throw a baseball, unless you're pitching and making it curve, generally your goal is to get the object there fast. So you don't want the ball to curve, you want it to go straight towards the target. So they usually put very little vertical speed on it, pretty much just like a line drive throw, a lot of horizontal speed. Okay. Any questions on that one? All right, so the example we're not going to look at is static equilibrium. And basically the idea here is that you have an object hanging from 2 cables, and the goal is to find the tension in each cable. Well, if the cables were vertical and they were spaced symmetrically on the each on each end of the box or the bar, or whatever it happened to be, then the tension would be half. Half the weight would be in one, half would be in the other. What complicates it here is that the cables are at different angles and they're different lengths. So once you make the cables different lengths, the tension in each cable is not necessarily the same. And the tension can add up to more than the actual weight of the object. Because, well, if you think of like lifting this table, if I were to pull at an angle and somebody else were to pull at an angle on the other side, the table would lift up. But unless we were both pulling straight up, we might create more tension. Like if there was a rope here and I were to pull kind of horizontal and the other person did, there'd be a lot more tension because we're pulling horizontal and up at the same time. Another way to think of that is if you cut one of these cables, what would happen to the weight? It would swing in one direction. So what that means is these cables are not only holding the object up, but they're also keeping it from swinging left and right. All right? So you might get more tension in the cables than the object actually weighs because of that. Right? But that's the idea of static equilibrium. It's a pretty straightforward problem to solve. You end up just making some triangles. And static from physics means everything's balanced. So the forces pulling left and right equal each other because there's no movement. And the forces pulling up and down equal each other. But that's the idea. All right, so results of force, let's go. All right, so for this part, can I see your packet? Is that last week's packet? So on page 344, thank you. to have you look at 25 to 47, just the odds. And then, let's see, 64, we're going to skip over that. And 66 and 69. So it's actually just 25 to 47 odd, 55, 57. Thank you. 55 and 57 are the word problems where they give you an object being thrown at an angle with a certain speed. Okay, so if you're watching the video from period 2-3, we're going to start now looking at the dot product, which is section 8.5, part 3. If you're watching the video from period 5-6, then your homework would be all those questions except 66 and 69. So you can just add 64 into your homework. Okay, so any questions on that? All right, so let me pause for a second so I can bring up part 3. All right, so dot product, 8.5, part 3. So we've done a lot of different things with vectors. We've added them, subtracted them, scaled them, find the length of them, but we've never multiplied them. And if you're thinking, well, didn't we do that when we did a scale? We did a number times a vector. And the answer was a vector. It just scales a vector. What we're going to look at in this section is a vector times a vector. So how do you multiply two vectors together? And when you do that, what do you get for an answer? Okay, well, the answer to the question mark in this section, I'll show you in a second, is going to be something. But in general, this question mark can be two different things. When you multiply two vectors together, you can get a number. Or when you multiply two vectors together, you can get a vector. The reason is there's two types of products with vectors. Today we're going to learn the dot product. Tomorrow or Wednesday, we're going to take a look at what's called cross product. Okay, so two different ways to multiply vectors together. Okay, I'm going to show you the formula for dot product right now. So in unit vector notation, you would have two vectors. The A's and the B's would all be numbers. Okay, and the formula to find the dot product, very, very simple. You're going to take A1, A2, multiply them together. Then you're going to take B1, B2, you're going to multiply those together. And then add. And that's it. So you're going to multiply the A's, the B's, and then add. Okay, so A1 is a number, A2 is a number. What do you get if you do a number times a number? Yeah, a number. B1 is a number, B2 is a number. What do you get if you do another number times a number? A number. And then if you take a number and add it to another number, you get a number. So the point here is the dot product is a number. Like 6, negative 12. Okay? That would be the kind of answer you would get for the dot product. What does that number mean? I don't know if we'll get to that today. But there is a use for that number, which I'll show you at some point. Okay, so here's two vectors. And we're going to find V dot W. And that's how you have to pronounce it. Don't say V times W. Why? because of what I told you earlier. If you said to somebody, I want you to find v times w, if they know anything about vectors, their next question would be, when you say times, do you want me to do a dot product, or do you want me to do a cross product? Yeah, because they're totally different. This is a dot product, it uses the dot symbol. A cross product would use the cross symbol, v cross w. But that's not what we're doing today. Okay, so what I usually do is just kind of lay it out first. Put down everything we're going to multiply. And Leo, can you tell me what two numbers would go in my first sets of parentheses to find v dot w?
2 and 5.
Yep, 2 and 5. And Dylan, my next two numbers?
Negative 3 and 3.
Negative 3 and 3. So we get 10, we get negative 9. 10 minus 9 is 1. So the dot product in this case is 1. Okay, let's try something a little different. Let's try w dot v. So Caleb, if I did w dot v, what would be my first two numbers this time in the correct order?
Negative 3, or 3 and negative 3. Right. Oh, sorry, no, 5 and 2
5 and 2, yep. And then the next two?
are 3 and negative
3 and negative 3. So now we did 5 times 2, negative 3, 3 times negative 3. What's the dot product there? Yeah, it's 1. So, based on example A and B, what does that mean about the dot product? I didn't prove anything, but this example suggests something, and what it does suggest is true all the time.
3. It's commutative.
It's commutative. Okay, so the dot product is commutative. Again, if you're saying, well, yeah, isn't multiplication always commutative when you switch the order? No. When we do a cross product, if you switch the order, you're going to get the opposite answer. So up until now, everything you've done with multiplication probably has been commutative. Changing the order didn't matter. And it still doesn't with dot product. But with cross product, it will. Okay, let's try v dot v. V dot v. So we'll go back up so we can see it. Okay, what would be my calculation for v dot v? Gracie?
2 times 2, or 2 and 2, plus negative 3 and 3, negative 3.
So we've got 2 times 2 plus negative 3 times negative 3. Before I do that out, what's another way of saying 2 times 2? Not the answer to, I know it's 4, but what's another way of saying 2 times 2? 2 squared. And if you think of that, you might see something that I'm trying to get you to see in a second. You squared the x component, you squared the y component, and you added them up. What's that kind of like doing that I showed you earlier? Yeah?
Pythagorean Theorem.
The what?
Pythagorean Theorem.
Kind of, but what didn't we do?
Square root.
We didn't square root it. So when you dot a vector with itself, it's kind of like finding the magnitude of the vector, except you don't square root it. That's the pattern. So 2 squared is 4, negative 3 squared is 9. So the dot product is 13. The magnitude would be square root of 13. So what could you call 13 in terms of the magnitude? 13 isn't the magnitude, but it's the, yeah?
The square?
It's the square of the magnitude, exactly. If you dot a vector with itself, you don't get the magnitude because you didn't take the square root. You get the magnitude squared. You don't have to call it w dot w, we didn't do that one, but it would work out the same. And if you look at that, you're like, well, why is that really important? Because in the formula that I'm about to show you, the formula I'm about to show you involves how to find the angle between two vectors. We're not going to get to that today. But in the next class, I'm going to prove where the formula comes from, and I need this result to do it. I can't get through the proof without knowing that dotting a vector with itself is the magnitude squared. This is kind of allows me to simplify something. Okay. For you guys, it's just more of an observation. We're not really going to use a proof at all. Okay, so let's try this dot product. We're going to dot the vector 2, 6 with 0, 0. What do I get when I do out that dot product? Right? 0. Can you be more specific? Like 0, like the number 0 or the vector 0? It can't be both. Number, right? Whenever we do a dot product, we said earlier, I said it, I didn't write it on this page, I did write it on the other page, but a vector dotted with a vector is a number. So the answer to this question is the number 0. Don't make it a bold 0, unless you were doing addition. If you add two vectors and get 0, absolutely, that's the bold 0. Okay, but this is a little different. Any questions on that? All right, so angle we're going to hold off on, so we'll finish up with that. So this is showing you that the distributive property works with dot product. You can do that, and it works fine. So u dotted with v plus w is the same as u dot v plus u dot w. Can I see your packet from this week? Any questions on that idea? Okay, so we're really almost done part 3, so that'll set us up pretty good for Wednesday. The last thing we have to finish in this section is how do we find the angle between two vectors? Okay, and that's what we'll start with on Wednesday. And part of the formula is the dot product. So I told you I'd tell you where the dot product's used. That's where it's used. All right, so the homework, it's going to be the same problems, okay, each night. And I'll explain what I mean. So I want you to do 7 to 17, but each question has 3 parts. All I want you to do for tonight is part A. Just part A, if you're in period 2-3. Part A is to find the dot product. Part B is to find the angle. Okay, we haven't talked about that yet, but if you do part A, you're going to be already halfway done the homework for the next time, which is parts B and C. Right? So just part A, if you're in period 2-3. If you happen to be watching this video and you're in period 5-6, you would have done the whole lesson. So for period 5-6, do the whole thing, including number 25.